So today we're gonna do some ZX simplification of diagram. You can go to the end of the video or just not put the noise or do both if you can handle it. But here it is. So let's say you have a circuit. So we initialize 2 qubits in the state 0 and 0. We made the Hadamard in the first qubit. After we proceed with this gate, so control gate. And so if you transform x in ZX calculus, the 0 became a black point, the Hadamard this, after you have this. No, it's a white one. To remember, just think that the complicated one is the black one and the simple one is the white one. Second qubit in this state. And yeah, so you have this. And you want to do some simplification about it. So one rule you can apply is the Hadamard, the identity rule, because if you do Hadamard, it is equal to the identity. So if you apply both time and Hadamard, which is a square, it's like you apply nothing. And we'll use that because you'll see after. That's a good trick for doing some manipulation. You do this up, you apply it also here, and it clearly does nothing. The fact is we want to simplify the diagram so it will help, but in reality it changed clearly nothing. Okay, after this we just use the color swap, which is that Hadamard with an X or Z gate is transformed in the other one. Well, here the white gate is a Z gate and the black gate is X gate, but so here we want to transform the white gate, so we just have Hadamard Z gate Hadamard, and it gives you X, and that's, I think, the main power of quantum computing, and that's the main power of ZX calculus. So yes, there is a video of Craig Gidney about that in this YouTube channel. So just apply this, and so you need to have on each branch a Hadamard to apply this rule. So you see we take this one, and this one, so there is one Hadamard on one branch and it will become a black one. So yes, that's it. Okay, and it remains as 2 Hadamards. Well, you can choose the Hadamard you want to apply the rule, so I can take this one, and this one, and just say, yeah, conserve those two. That's literally the same. Just choose the adamar you want. So as I told you, we still have a adamar. Okay, and here um, how can I proceed? Um, yeah, let's put it there. Well, I just did some bullshit because this Adamar is not here again. So you just have this and this and this. Okay, okay. Okay. While I'm doing this, and so that's it. And so now I will use the rule of color swap, which is that of fusion, that if you have two white balls, like if you have two Z, it will give you Z. If you have two X, like if you have X squared, it give you X. So it means because Z gate is a black gate and is a white gate and the X gate is a black gate. If you have two black gates, become one black gate, and if you have two white gates, it becomes one white gate. So you write this to this and you proceed like that. Okay. Okay. What I'm doing. So yeah, you just fuse this one on this one, and this one on this one. So by fusing them, you just arrive to this. Like this. This goes there, this goes there, this goes there. So this is a representation of all of this. And so you still have another marker, and you still have here your line. It's important line because X gate with two lines is an identity on the Z gate too. So here you arrive, you apply the color swap like this one. H sets HXH is Z, so HXH is Z, so it becomes a white gate. And yes, arrive to this. And now you just have to apply the identity rule, which tells you that this is just this, and that this is just this. So it uses identity rule, and so you just have this And what you can see, it's like you can, like in the ZX calculus, there is no like this equals this equals this. There is no, if you have no, there is no format, like you can write it as you want. And I just want to show you that's this. So it just the cap. So we just prove that this circuit is equal to the cap. That's it.